It is no surprise that physics is a heavily math-based science. In fact, among all of the sciences, physics might be the one that requires the most math, especially if you decide after your degree to go into a master or PhD program. But how much math do you actually need in order to get a bachelor degree in physics? Today, I want to talk to you about what are the minimum requirements, or what I think to be the minimum requirements for you to earn a degree in physics. In the process, I'm going to share with you some of my experiences, and I'm also going to tell you what some of my favorite books or textbooks are for each subject. Now, I want to preface this by saying that I do not get any money from any of the publishers. I'm not sponsoring anything. I'm just relating with you guys what I think to be the best textbook and sources in order to study science and math from. So let me say from the start that I assume, hopefully we all agree on this, that everyone should have already under their belt algebra, geometry, and trigonometry, and pre-calculus. That should be, in my opinion, the minimum required for any degree, even if you're not graduating with a degree in science, and especially in physics. So starting from that background, what is the first thing that you should do? Well, generally, there's a tendency to try to get done with your degree as soon as you can, mostly because most people pay for their degree and they don't want to spend a lot of money. So students tend to take math classes at the same time as physics classes. And that's not a problem. It's not a mistake. As long as you make sure that once you take a physics course, you already have the mathematical knowledge required for that class. Now, in some classes, they say it would be best if you knew this math beforehand, but if you don't, it's okay because, you can learn the basics um, while you're taking the physics course. I strongly disagree on that. I actually think that the best way to do it would be to have the math courses lead by one semester. And what I mean by that is if you take a physics course that requires Calc 1, you shouldn't be taking Calculus 1 while you're taking that physics course, but you should already have Calculus 1, even if your instructor says, we're going to cover the basics of Calc 1 in the class, so you don't need to actually know it. Because think about it from a logical point of view. If it takes 4 or 5 months to learn the basics of Calculus 1, then there's no way for you to actually learn them in a 2-week review in a physics course. So you're not really going to learn calculus, and the fact that you don't have math, it's actually going to make you struggle with the material. What I always tell my students is math should be the tool with which you solve physics problems. It should not be an impediment. If you struggle with math, that's going to put you behind doing the science. So if you can, you should always take the math courses first and then move on to the physics courses as needed. So clearly, the first thing you need to know is calculus. And by this, I mean Calculus 1, Calculus 2, and Calculus 3. These 3 classes need to be taken into this sequence. Calculus 1 generally is the basics, the introduction to limits and derivatives and integration. There's a lot of proofs. That's the basics, and you should learn it as much as you can. Calculus 2 is generally known as the integral calculus. It's that class where you do 4 or 5 months of integration and you learn all of those integration techniques, which are fundamental to science. I know most people hated Calculus 2 when they took it. That's what my students tell me. That's what my classmates used to tell me. I loved it. I loved it because doing derivatives was very mechanical. You learned the power rule, the chain rule, the quotient rule, and once you learned those, essentially you knew how to do every derivative. But integral calculus really required skills and experience because some of the integrals, even though you might have known all the methods, were really tricky to solve, and that was part of what I liked. And Calculus 3 is generally what is known as vector calculus. So it's essentially Calculus 1 on steroids, Calculus 1 in 3 dimensions. And it's a beautiful subject. You're going to talk about motion also, which relates to physics in 2 and 3 dimensions. You're going to do a lot of 3-dimensional calculus and vector fields, which are important when you study electricity and magnetism. And then you're going to study those beautiful theorems like Gauss's theorem, Stokes' theorem, Green's theorem, and all the properties of vector fields. Okay, so my favorite book for that class, I have it here. Again, I'm not sponsoring anything, is Calculus by Stewart. I'm pretty sure this is the book that every single student in the world used to learn calculus from. It's an amazing book. Now, it doesn't matter which edition you buy. All the editions are essentially the same, but this is one of the books that I personally loved more than anything else, because I bought it 2 semesters before I knew I was going to take calculus, and I went through it myself. And I actually went through this book from front to back, and I did all the problems, and I have all my notebooks with all my homework problems saved in a shelf behind me there. So this is the first book you want to get, or something like this, Learn Calculus. So I will say, if you're taking Calc 1 and you have to take a calculus-based physics, take Calculus 1 first. Don't take them at the same time. Always let the math lead by one semester. Okay, take Calculus 1 first, then take physics. Once you start taking physics, then you will be taking Calculus 2, and Calculus 2 will be useful in, say, your Physics 2, where you study generally electricity and magnetism. Okay, another very important subject, which is an extension to that, is something not really needed, but I did it, is vector analysis. So it's essentially a little more advanced stuff in vector calculus, three-dimensional calculus, and I learned it from this. This is an introduction to vector analysis by Davis and Snyder. Beautiful book, very short, has a lot of derivations that are mostly physics justified, or heuristic derivations that are justified on scientific grounds. So it makes more sense from the point of view of someone who studies science. But there are a lot of beautiful advanced vector calculus theorems, transport theorems, and so on and so forth. Very useful, very good also as a reference, because it's a short book. Then what else? Well, if you're graduating in physics, you need to know quantum mechanics. One of the most important things in quantum mechanics is that you need to know how to work with vectors and matrices. So that is the language of linear algebra. So linear algebra is one of those classes that you should learn. I learned it from this book. I know it's pretty famous. It's Linear Algebra, A Modern Introduction by David Poole. It was a pretty good book. I think the explanations were very clear, lots of examples, lots of exercises. Honestly, I think any good linear algebra book would do the job. But it's a very important subject, and let me tell you why. When I took quantum mechanics, I had not taken linear algebra before. I had just transferred to my institution, and my advisor, who wanted me to graduate quickly, said, don't worry about taking linear algebra before quantum mechanics. Take quantum mechanics and linear algebra at the same time. But quantum mechanics, for those who might know this, it's all about vectors and matrices. The state of a system is defined as a finite or infinite dimensional vector, and the operators that act on that state are matrices, n by n matrices, or infinite dimensional matrices. So if you don't know how to work with that stuff, you're completely lost. So the first time I took quantum mechanics, I did not understand anything. Partly was because quantum mechanics is conceptually hard, but what made it a lot harder was the fact that I did not have the math. So every time we learned something, I was just struggling to catch up with the math, to read a very brief 3 or 4 page review on something, on orthogonal matrices or this or that related to linear algebra, because I didn't know how to even solve an eigenvalue problem. Okay, so because you have to take quantum mechanics, try to take linear algebra before you take quantum mechanics. Now, another important subject is differential equations, and the reason is very simple. All the laws of physics that we know of are all some sorts of differential equations. Think of Newton's laws. They're differential equations. Think of Schrodinger equation. It's a differential equation. The wave equation, the heat equation. So you need to know how to solve differential equations. There are 2 types of differential equations. There is ordinary differential equations, also known as ODEs, and partial differential equations, which are known as PDEs. So for ODEs, I used what is I consider to be my favorite book of all time in math and science. Okay, this is a very old book by today's standards by Tenenbaum and Pollard. It's a Dover book. It's very cheap. I think I bought it for $10, and it's just called Ordinary Differential Equations. It's this little blue book, and I actually used to call this the Holy Scripture of ODEs. And this is really one of those books that I read from cover to cover. It's beautiful, it's clearly written, it's rigorous, has tons of examples. Everything is explained step by step, and the problems range from very simple to very challenging. And it covers nearly everything you need to know about differential equations. Literally any single topic that you can think of for ordinary differential equations is in this book. Okay? So beautiful book, very hard read, I have to say. Not hard in the sense that it's hard to read, in the sense that it's a beautiful read, but it demands a lot from the reader. This is not something that you can read in your leisure time for 15 minutes. You really have to put the time into it. And I think it took me about 9 months to go through the entire book and do nearly all of the problems. But it paid because, like anything that is worth in life, that it's worth something, it requires a lot of effort. Now, why do we have ODEs and PDEs? Ordinary differential equations are differential equations that essentially are in one variable. Now, you can have things more complicated, like the wave equation, the heat equation. These are equations in which the function that you're trying to solve for may depend on 2 or 3 variables, and that is the realm of partial differential equations. The difference in level of difficulty between ordinary differential equations and partial differential equations is so gigantic that the two topics are taught completely separately. So the book I learned it from, which I sort of liked it, is this one here, is Partial Differential Equations, an Introduction by Walter Strauss. It's a small book, very similar to the vector analysis book that I showed you. I have to say it lacks clarity in some of the sections, but it has a lot of good examples, most of them that relate to physics. Again, the basic equations that you study here are equations that come from physics. So it was a good read. I'm sure there are better books out there, but this is what I did. But definitely this is one of the classes you want to take. And I have to say, partial differential equations, especially if you are thinking of going to grad school for physics, you will need to know how to solve partial differential equations regardless of what field you go into. Okay, these are all the basic subjects, and then there are a couple more subjects that I think you should study if you're really serious about physics. One of them is complex analysis. And essentially, complex analysis, also known as the theory of complex variables, it deals with functions of complex, namely real and imaginary um, arguments. It's a beautiful subject. It's beautiful in itself, just if you're interested in mathematics and you want to learn about it more. But this is a very, very, very beautiful subject that I think any physicist should know, especially, once again, if you go into grad school where you will do quantum field theory, you will have to do a lot of integration in the complex plane. And you have to learn this stuff if you want to learn how to do those integrals. This is the book I used. As you guys can see, I like the Dover books. I think they're pretty good. They're cheap. They have generally very good books. It's called Complex Variables, Harmonic and Analytic Functions by Flanigan. And this has a sort of an extra in it because it also talks about harmonic functions, which are generally not necessarily discussed in complex variable. Again, extremely clearly written, lots of examples, lots of problems in each section, and has most of the solutions in the back. And then the last topic, again, especially if you think of going into graduate school for physics, you will have to take, maybe if you go into theoretical physics like I did for particle physics, you have to take something called group theory. And at the institution where I graduated with a degree in math first. They were not offering group theory, but they had Abstract Algebra, which is the mathematical foundation for group theory. So I took that class. I struggled a lot. It was really hard for me. It's definitely not my cup of tea. I didn't appreciate it the first time I took it because it's very abstract, as the name suggests. It's completely different from calculus or differential equations where you actually feel like you're solving a problem, that it's a physical problem. Abstract algebra deals with abstract object in an algebraic setting. But then when I relearned it on my own, the things that I had learned in class the first time really started to make sense. The theory of groups, finite groups, rings, fields, and so on and so forth. The book I used was this. I'm just telling you this one here because it wasn't the best book I've used, but this is the only one I used, and I don't know any other source. I guess it was okay. Again, it was a cheap book. I used it just to learn the basics. You don't need to know all of abstract algebra in order to use it in physics, but that's what I used. But then clearly you cannot learn all of the math out there. So eventually I can tell you from experience that you will end up forgetting some of the math that you learned, and you'll need a book as a reference. So one way of doing this is to just, keep all of those books there with you all the time and reference those. But it can be pretty hard because if you're like me and you don't have a good memory, you're not going to remember every single thing in every book. So you can buy something called a Mathematical Methods for Physics book or for science. And if you go to grad school, you might have to take a class based on mathematical methods for physics and science. So you can buy one. The one I used in my graduate course for math methods for physics and engineering was this one here. Excellent book. Now, this is not the kind of book that you want to read, okay? It's probably, let's see, it's about 1,300 pages. So this is not something that you read, but it's something that you can keep as a reference. It has nearly any single topic in math that you can think of. Now, of course, it's compressed. It doesn't go into details as much as each textbook individually does, but all the info that you need, you're probably going to find it here if you just want to glance at things. And this is, calculus, algebra, trigonometry, geometry, differential equations, partial differential equations, linear algebra, complex variables, probability and statistics, anything that you can think of, tensor analysis, calculus of variations, which are slightly more advanced topics. It's all in here. Fourier analysis. So whatever you need to learn, you have it in here, and it's a really good reference. As a matter of fact, this is the book I keep on my desk if I'm working on something and I need to quickly reference something. I just open the book and I say, oh, okay, this is, the associated Legendre function for integer L, for instance, okay? So it wasn't very expensive, as I recall. I generally tend to buy used books anyhow, and I think everyone should do that. I tell that to my students as well, so you can always find a cheap copy. Okay, so this was my list. It's not a comprehensive list by any means. I'm sure you can learn a lot more, but the key here is you want to have an idea of what you need to study, at least at a basic level, in order to have a package of mathematical tools that allow you to approach and solve physical problems. Now, there are a lot more topics that you can learn, and that's really up to you. It depends on how much time you have, on how much financial possibility you have, and what are the things that you really want to learn personally. Okay, so I'm going to put a list of the books and the topics in the description of the video below. Let me know what you guys think.